So the next group of functions we're going to look at as far as derivatives are concerned are hyperbolic functions. This is probably something totally new for most of you, perhaps not. Recall that Leonard Euler discovered in the 1700s the constant that was later named after him, Euler's constant, by recognizing its appearance in many applications in science and finance. He also noticed that certain even and odd combinations of the exponential functions, e to the x and e to the negative x, appear so frequently in application that they've been grouped together and been named the hyperbolic functions. Whenever entities such as light, velocity, electricity, or radioactivity are gradually absorbed or extinguished if they're shrinking, the decay is represented by hyperbolic functions. Another application is the description of ocean waves, and perhaps the most famous application is something called the catenary. And the catenary describes the shapes of hanging wire, like power lines or suspension bridges, and this is a pretty important calculation, especially as we joke about engineering students building bridges that we don't want to drive over if they didn't do good in calculus. All right. In many ways, hyperbolic functions are analogous to trig functions, and that's because they have the same relationship to the hyperbola that trig functions have to the circle. So each of the individual hyperbolic functions reflect or mirror the trig function. So for example, we have hyperbolic sine, hyperbolic cosine, hyperbolic tangent, all 6 functions hyperbolically. Okay? Now, the way that we define them, again, is with Euler's constant. Okay? So for example, hyperbolic sine of x equals e to the x minus e to the negative x over 2. Hyperbolic sine equals e to the x minus e to the negative x over 2. Hyperbolic cosine equals e to the x plus e to the negative x over 2. Notice everything else is defined in the exact same way that trig functions are. Tangent equals sine over cosine, cosecant equals 1 over sine, etc. So you really only have 2 hyperbolic functions to memorize, and that's sine and cosine, and then you can apply the ratios that you know from trigonometry for the rest. Okay? We can see the graphs of hyperbolic sine and hyperbolic cosine by doing graphical addition, right? So remember that hyperbolic sine is e to the x minus e to the negative x over 2, or we could write it as 1/2 e to the x minus 1/2 e to the negative x, and we could see those 2 parts, and then when we add them together, we get this S-shaped curve, almost like a cube for the hyperbolic sine. Doing the same for cosine over here, 1/2 e to the x, where am I at? Here we go. 1/2 e to the x plus 1/2 e to the negative x, and what I get is a parabola. Okay? And then over here to the right, you see the catenary with its equation. That we see the velocity of a water wave with length L. This is the wave that we were talking about it modeling, and specifically it's just shrinking, etc. Like the trig functions, hyperbolic functions satisfy a number of identities, but be careful here, because these are similar, they're not the same. These are similar, they are not the same, and you'll see here. So the sine of negative x equals the negative sine of x. Okay? The sine of negative x equals the negative sine of x. This is not true in cosine. And the cosine of negative x equals the hyperbolic cosine. I should be saying hyperbolic for all of these. None of these are trig function. All of these are hyperbolic. So this is hyperbolic sine, hyperbolic cosine, hyperbolic tangent. Okay. Here we have hyperbolic cosine squared minus hyperbolic sine squared equals 1 instead of plus 1 minus hyperbolic tangent squared equals secant squared, etc. And then we have the sum of two angles. The hyperbolic sine of the sum of two angles equals the hyperbolic sine of the first times the cosine of the second. Excuse me. Plus the hyperbolic cosine of the first times the hyperbolic sine of the second. Okay? Alright, so you can look back at those and copy those down as well. So let's do a proof. I believe that is Socrates there. I'm pretty sure it is. 'Cause I think he's the one that came up with proofs. So we want to prove that hyperbolic cosine squared minus hyperbolic sine squared equals 1. So let's just rewrite those into the definitions we were given using Euler's constant that you can see right under Socrates. All I've done here is substituting these values in and then squared them. If we FOIL those out, in the numerator we get e to the 2x plus 2 plus e to the negative 2x all over 4, 2 squared is 4, minus e to the 2x minus 2 plus e to the negative 2x over 4. And what we see here is that these are almost everything's canceling out except the 2's. E to the 2x minus e to the 2x, e to the negative 2x minus e to the negative 2x. Both of those cancel out. So we get 2 minus a negative 2, which is a positive 4 over 4, or it equals 1. So again, we did prove that by just doing some algebraic substitution on the right. One second, please. So the Pythagorean identity can shed some light on why these are hyperbolic functions. Okay. Remember from trigonometry, if t is any real number, notice that point P lies on the unit circle x squared plus y squared equals 1, where t is the radian measure of the angle POQ and twice the area of the shaded region. Okay, trig functions are called circular functions for this reason. Okay, and twice the area of the shaded region. Okay. Hyperbolic, here's a hyperbola graph. Okay. If t is any real number, notice that point P lies on the right branch of the hyperbola, x squared minus y squared equals 1. And t is twice the area of the shaded region. So these functions are called hyperbolic functions. And so you can see a little bit of the correlation between trig functions and hyperbolic functions. So again, if we use the definition of hyperbolic sine up in the right corner in green, we could use that to find the derivative. Remember, here we have 1/2 times everything, so we can leave the 2 in the denominator because that's our coefficient rule for derivatives. The derivative of e to the x is simply e to the x minus the derivative of e to the negative x. Notice now we have a function in the exponent, so our derivative is e to the exponent and then the derivative of the exponent. So it's e to the negative x, but then the derivative of the exponent, negative x, is negative 1 times all of this. And so it's a negative times a negative, so it becomes plus. And so notice that what happens when we take the derivative of the hyperbolic sine function, the negative in the numerator turns into a positive, and if you look back to our original charts, e to the x plus e to the negative x over 2 is simply the hyperbolic cosine function. Again, you could prove all of these in a similar way. The derivative of hyperbolic sine is hyperbolic cosine. The derivative of hyperbolic cosine is hyperbolic sine. And so on. I'm not going to go through these. You do need to know most of these, although typically sine, cosine, and tangent are the ones that we see most readily in functions. Okay. So the other part we have to look at is inverse hyperbolic functions. Okay. So remember that hyperbolic functions are defined by Euler's constant, or specifically that they are exponential functions. And so if the original function is an exponential function, what would we expect the inverse to be? What is the inverse of an exponent of an exponential function? It's a logarithm. Okay, so the inverse hyperbolic sine is equal to the natural log of x plus the square root of x squared plus 1. Notice the inverse hyperbolic cosine is similar, except in the radical there's a negative, so I have the natural log of x plus the square root of x squared minus 1. And then the hyperbolic tangent is 1/2 times the natural log of 1 plus x over 1 minus x. And here you see some of the graphs of each of these pieces. All right, you can stop here if you want to look at those a little closer. I don't really have much to add. So this is one of the key things that you really need to know is the derivatives of the inverse hyperbolic functions. You need to be able to use these in solving problems. I'm not going to walk through them. We've touched on them and how you even get them. So let's look at a problem here. Again, notice there's a little video icon here. I think most of the last lectures have had videos around all the examples in the chapter and section. So if you don't like my explanation, you can always go back. Alright, so again we have a chain rule here. We have the hyperbolic tangent of a function. So we're first going to take the outer function, which is the hyperbolic tangent. We're going to plug it into this formula. So the derivative of the outer is going to be 1 over 1 minus the argument squared. In our example, the argument is the natural sine of x. So we're going to get 1 over 1 minus sine squared x. Okay, times the derivative of sine squared x, the derivative of the argument. So we take the derivative of the outer function, which was the hyperbolic tangent function, times the derivative of the inner function. And well, the derivative of the inner function is simply cosine x. Okay? Hopefully you recognize in the denominator of this function that we have 1 minus sine squared, which is actually equal to cosine squared. Cosine squared plus 1 plus sine squared equals 1. So cosine squared equals 1 minus sine squared. So we do that last substitution. We get 1 over cosine, or specifically secant x. All right. So the derivative to our function here actually ends up being a trig function. Okay. So there were a lot of formulas that you needed to know here. The hyperbolic functions, by definition, what their values are. Remember, again, you only need to know the sine and cosine. And then you need to know all the derivatives for the hyperbolic functions. You need to know the definition of what an inverse sine is in terms of the logarithm, inverse cosine, not inverse, hyperbolic inverse cosine, and then also hyperbolic inverse tangent, and then also know the derivatives of all of those pieces. Okay, so there's quite a lot of memory involved in Chapter 3, and certainly at the end of Chapter 2. My biggest recommendation is write them down, and write them down frequently. If you can spend 5 minutes writing down some of these formulas, I think it's better than just reading through them and especially waiting for the test.